I mentioned that one of the reasons that Mars might lack a substantial atmosphere these days is because of its lack of a magnetic field. A magnetic field can provide protection against the solar wind coming in and knocking particles off. The obvious question to ask, though, is why does Mars not have a magnetic field? The simple answer is Mars is smaller than the Earth. It's about 1/10 of the mass of the Earth, and you can imagine that a magnetic field is something that requires a molten liquid iron core, and that with Mars so much smaller, so much less massive, core freezes out, no more magnetic field, dead. But the answer has to be more complicated than that. Venus doesn't have a magnetic field, and Venus and Earth are nearly the same size. Mercury, significantly smaller than even Mars, big magnetic field. Jupiter's moon Ganymede, an icy moon, magnetic field. Jupiter, big, huge magnetic field. So there's something else going on besides just big things have magnetic fields, small things don't have magnetic fields. In the case of Venus and the Earth, the answer is thought to depend on water, the lack of water on Venus. Let's think a little bit more carefully about what you need to make a magnetic field, and then we'll look at Venus first, and then think harder about Mars itself. Okay, so I said that we need a liquid iron core. Well, yes, it's true. The way you get a magnetic field inside of a planet is from having a conductive liquid on the inside, which is moving through a magnetic field, which amplifies the magnetic field, which is the magnetic field that's being amplified in the first place. It's a whole chicken and egg magnetic field movement problem, but that's just called a process of a dynamo. It's a self-generating magnetic field inside of a moving, conducting liquid. So when I said that we needed a molten iron core, that's one part of it, but we need that iron core to be moving. How do you make a core? How do you make that core move? How do you make the material inside that core move? You do it from convection. The simplest way to think about convection in this case is, you have your pot of water on a flame and you heat the stuff on the bottom and it gets very hot, and the hot stuff rises up and the stuff on the top cools, it goes down, and you have big convective sails of water, in this case, on top of your pan on the stove. But what if instead of heating the water this way, you put it in, say, a pressure cooker, and you enclose all the sides of it? You still heat it, but you enclose the top of it too, and you heat it maybe from all sides. Maybe you heat it in the oven instead. What is going to happen to that stuff on the inside? It's hot, it's molten, well, it's water, okay, of course it's molten, but it's not hotter on the bottom than it is on the top. It's not hotter anywhere than it is anywhere, and so it's relatively static. It's not moving. This is a key point. To have convection, therefore to have a magnetic field, you need both the liquid that's moving, and you need something that's hot on the bottom and cooling on the top to drive that convection. And this is where you get the big difference between the Earth and Venus, even though they're the same size, and they may even be the same temperature on the inside at where their cores are, but the Earth cools very efficiently through the process of, among other things, plate tectonics. You take cold stuff at the top and you dump it down inside the mantle of the Earth. This is a plate subducting down inside of the Earth. More stuff comes back on top. The hot stuff comes back on top. This is the process. If you had a big turkey and you wanted to cool the big hot turkey, well, you could just let it cool, or you could slice it open, take some of the hot stuff, turn it up upside down, and that cools. Do it again, do it again. It's a much faster way to cool things, and that drives very vigorous convection. On Venus, this doesn't happen. There are no plate tectonics on Venus, and instead you just have that turkey that's not being cut open. So you have what's called a stagnant lid, and that stagnant lid, maybe it makes the interior hotter because you're keeping it warm on the inside, but you don't have as big a temperature gradient across here, and that temperature gradient is what causes the convection, which in turn helps to make that magnetic field. And then, of course, you might ask the question, why does Venus not have plate tectonics? And I think the answer to that is that it requires water. This process of plates dropping down in through here and bending and subducting requires lubrication. That lubrication comes from the oceans where all of this is happening. Venus, with its runaway greenhouse, lost its liquid water billions of years ago, and possibly, as a consequence, ended up having a frozen solid surface, stagnant surface, shutting off its own magnetic field. Is that the entire story? Probably not. Mercury doesn't look like Mercury has plate tectonics, so that argument kind of goes away from Mercury. Ganymede plate tectonics? No, I don't think so. But this is at least one way to sort of think about how a magnetic field happens. But the first part is we do need that molten iron interior, molten conducting interior, or we're not going to have a magnetic field no matter what. So, do we know if Mars has something like that at all? First, you can simply measure the density of Mars. You can measure the volume by seeing how big it is. You measure the mass. Well, it was easy to do once the moons were discovered. You look at the moon going around Mars and you see how long it takes to go around Mars. You see how far away from Mars it is, and you use very simple Kepler's laws to get the mass. With a spacecraft, you can track it very precisely and do even better. And we now know that the density of Mars is 3.935 grams per cubic centimeter. 3.935 grams per cubic centimeter. To calibrate, a typical rock is somewhere around 3 grams per cc. Ice is about 1. And to get these higher densities requires something higher density than just your typical rock that you can pick up. What is that thing? Well, could be iron. Could be an iron core. How do you do a little bit better? You measure the rotational moment of inertia of the planet. Let me remind you what the rotational moment of inertia is. You have a round thing like this. You take it, you spin it, and you see how much torque it takes to spin it up to a certain speed. Something that has a high moment of inertia is harder to spin up than something that has a low moment of inertia. How do you make the moment of inertia high? Well, you can imagine that instead of having this nice uniform planet like this, what if you had all of your weight on the outside, so you almost were a ring instead? That would be the highest moment of inertia way to distribute the same mass. How do you make the lowest moment of inertia? What's the easiest thing to spin? Well, what if instead you took all of your mass and you just put it right there in the middle? That would be the lowest moment of inertia. The moment of inertia of Mars has been measured in the units that we use for these things in planetary science. You do moment of inertia divided by the mass divided by the radius squared, and that's equal to 0.366. What do you do with that number? Well, you might actually remember from elementary physics or even calculus that you probably calculated the moment of inertia for a uniform like this. And that moment of inertia for a uniform sphere was I over mr squared equals 2/5, which is 0.4. So if Mars were purely uniform, nothing else interesting going on in the interior, it would have 2/5, 0.4. It's a little bit lower. A little bit lower, remember, to make it lower, you put things in the middle. This is evidence already that there is a core going on in the interior of Mars. What do you do next? Well, you take detailed models of what you think the composition of Mars might be, and you go into the lab and experiment by compressing them. We'll talk a lot about this when we talk in our next unit about giant planets. You compress them and you figure out their equation of state. Equation of state meaning how dense they are given a certain pressure, because even the rocks that are 3 grams per cc at the surface, you compress them and they'll go up in density, so you have to figure that out, and then you add in some sort of iron core on the interior, and you construct an artificial planet. You measure the moment of inertia of that artificial planet. You keep the density of that artificial planet to be 3.935, and you see what works. And when you do that, you can make plots that look something like this. And here are models of the interior structure of Mars. The interior structure of Mars starts out, here's the surface of Mars, and here's the center in through here, and you can see at the surface there is typical rock, crustal rock, 3 grams per cc. After about 50 kilometers of crust, though, there is the material in the mantle, which is higher density material, and continuing to go up in density as you compress it. The pressure is down through here, and eventually you get to a core. And one of the problems with Mars is we don't know what the core would have been made out of. A pure iron core could be pretty small, and it would be here if we extrapolated. So Mars could look like this, or it could have the iron in the core in the form of Fe3O4, and then it would have to look like this. All of these different models give you the right density and give you the right moment of inertia. And importantly, for typical materials that we think should be in the interior of Mars, all of these models give you a conducting core. So the answer, we think, is that Mars indeed has a core. Is it liquid? Is it still liquid? Did it cool down so fast that it's now solid? We don't know the answer to that. But there's one thing we know, which is that it absolutely was liquid at one point. And here's how we know. There is substantial remnant magnetism in the crust of Mars that's been detected by the Mars Global Surveyor spacecraft as it was flying over the surface of Mars. This remnant magnetism is the sorts of magnetism that happens when, say, volcanic material solidifies in the presence of a magnetic field. And this remnant magnetism is 100 times stronger than any magnetism in the crust of the Earth's magnetic field, where the same sorts of things are happening all the time. And this remnant magnetism, if you look very carefully, does not cover the entire planet. The remnant magnetism is not really up here in the Amazonian materials that you see through here. It's not over here in the volcanic regions really at all. It's only in the ancient terrains. Pretty clear evidence that Mars had a magnetic field back at least in the Noachian time. There's more to it than just remnant magnetism. There's something particularly strange going on with this remnant magnetism. Look at these stripes. This is positive magnetism, magnetic field coming out of the crust. This is the blue is negative, positive, negative, positive, negative, positive, negative. Stripes going across, huge stripes going across the entire planet. And, well, it's hard not to look at that and find it reminiscent of the same sort of magnetic striping that happens in seafloors on the Earth that are spreading due to plate tectonics. Let me draw you how that looks. At the center of, say, the Atlantic Ocean, there are two plates that are moving apart from each other, and as they move apart, new magmatic material comes up from the interior and solidifies. So as time goes by, this material that came and solidified from here, it starts to, this part moves this way, this part moves this way. So this material moves to here, this material moves to here, and new stuff is created in the interior. Time goes by, the same thing happens. This stuff continues to move to here, this stuff breaks apart, moves to here. This is supposed to be blue. Red stuff moves to here, and let's say the green stuff appears in the middle. This is the progression of time going on through here. This is the sequence of recently solidified seafloor material. Whenever the seafloor solidifies, the imprint of the Earth's magnetic field is left inside of it. And so that's one of the ways you can see what the magnetic field of the Earth has been doing over the past 250 million years as these seafloors have been spreading. And what has the Earth's magnetic field been doing? Well, one of the things it's been doing is flipping directions. The north pole of the magnetic field flips around to the south pole and vice versa. So you look at these things and you say, oh, look, here it's pointing downward. Here it might be pointing upward, symmetric on both sides, back downward again. And this was one of the key observations that led to the hypothesis of plate tectonics. Now let's go back to Mars. And you can see why, look at that. It sure looks like that positive, negative, and big linear stripes of it. What's more, if this really were plate tectonics, it would be that the spreading was going, sort of this direction. It's hard on a three-dimensional map to figure out exactly where it goes. This direction and this direction. And, well, look at this. Look at these. We never really talked about these three volcanoes all in a very perfect row like this. This is the sort of thing that you get on the Hawaiian island chains. As the seafloor is spreading and moving over a hotspot, you get progressively different locations for those volcanoes. Now, maybe later on, as the plate tectonics died away, Olympus Mons then formed here in this one spot, and the plates never moved. Is it true? I will say, like I say about almost everything, it seems like, that I'm skeptical. I was very skeptical, and then a very strange thing happened. Last night, literally last night, the night before I was about to film this particular lecture, and I was thinking very hard about this problem, I went out to dinner with some friends, and at dinner, unannounced, was Jack Connerny, right there. And I asked him, I said, so plate tectonics, yes or no? And he said, it's very controversial. Most people don't believe it. And then he went on to explain why those most people are absolutely wrong. He said that there's really no other process that can explain the striping, and that would also have, it's that makes it just a coincidence that this is perpendicular to the striping. There are big transform faults that are perpendicular to the striping. The main complaint about the interpretation of this as plate tectonic is that in plate tectonics, you don't just have the seafloor spreading, you need to have it subducting. And on the Earth, you get these dramatic subduction zones like the Marianas Trench, which go down, and those should be somewhere. You don't see them on Mars. To be fair, this would have been 4 billion years ago, and a lot has happened, as you can see, in the north in 4 billion years that has erased everything else going on. So the one other big argument that Jack Canary uses is that, look, there is remnant magnetism here. There is striping. There are large regions of magnetism. That means that there had to be huge amounts of crust, of that frozen magma being formed. Plate tectonics on the Earth is the most efficient way to make this sort of crust. On Mars, maybe yes, maybe no. I still don't know the answer for sure, but I can tell you that there's at least one person who is dead certain that this is evidence of ancient plate tectonics. Why would those plate tectonics have stopped? Well, maybe the same reason on Venus. Maybe there was not enough water to keep it lubricated. For a while it happened, and that those plate tectonics would have allowed for very efficient cooling. Cooling is great because it allows convection. Convection is great because it allows magnetic fields. But as this plate tectonics shut off, this stagnant lid developed, the magnetic field of Mars would have stopped. When did it stop? Well, again, we don't see it in the Amazonian materials. We don't see it even in these sort of middle stage volcanic materials. We only see it in the very ancient things. There was definitely a magnetic field in the ancient past. There definitely isn't now, and we sort of can see the history here. Even if we don't know exactly why it stopped, we certainly can see when it stopped. And that lack of a magnetic field could be a big part of the story why we have such a small atmosphere there today.